Welcome back, ladies and gentlemen. We are on section 12.3, day 2, estimating the parameters, constructing a confidence interval for the slope. By the end of this lesson, you'll be able to interpret the values of A, B, S, and the standard error of the slope in context and determine these values from computer output. You'll also be able to construct and interpret a confidence interval for the slope beta of the population true regression line. Go ahead and try these problems when we're done with our lesson. Let's begin. So as stated, we are in section 12.3, day 2, confidence intervals for beta. You can find much of this information on these AP daily videos in the AP classroom. And you can also read this information on pages 820 to 825 in our textbook. Let's start with the question of what are the 3 parameters that we need to estimate in a regression model, and what do we use to estimate them? Well, the 3 parameters are alpha, beta, and sigma. Alpha is the population y-intercept estimated by lowercase a, which is the sample y-intercept. Beta is the population slope, which is estimated by lowercase b, which is the sample slope. And sigma is the population standard deviation estimated by s, which is the standard deviation of the residuals from the sample data. And this particular value measures how far the dots are from the line. Now, what is the standard error of the slope, and how do we interpret it? And finally, is it on the formula sheet? Well, the formula is that the standard error of the slope is equal to the standard deviation of the residuals, s, divided by the standard deviation of x times the square root of our sample size minus 1. The interpretation of this value is how far the sample slopes typically vary from the population slope. And yes, you can find this on the formula sheet, but you're unlikely to need it. Usually you're given this value in computer output. Now, what is the formula for constructing a confidence interval for a slope? Where do you get the value of t star, and how many degrees of freedom should we use? Well, the formula is our statistic plus minus our critical value times the standard error of our statistic. In this case, our statistic is the sample slope. So we're taking b plus minus t star, which is our critical value, times the standard error of the sample slope. Now, t star times the sample error of your sample slope is your margin of error. Now, degrees of freedom, because we're dealing with 2 variables, we're actually going to take our sample size minus 2 instead of minus 1 like we would have done with like chi-square tests. In this case, we're just going to take our sample size minus 2. Now, t star, we calculate from inverse t, or we can use the t table. This is not going to be from the computer printout or the computer output. The computer output shows the t that's calculated for a test, not an interval. All right, so remember, it doesn't show the star, so it's not the right t. All right, so let's go ahead and take a look at an example. So is there a relationship between time spent at a buffet and the amount of tip? Charlotte, an AP statistics student who worked at an Asian buffet, decided to investigate this question. While she was doing her job as a hostess, she obtained a random sample of 12 receipts, which included the length of time in minutes the party was in the restaurant and the amount of tip in dollars. Computer output is shown below. All right, so we have our y-intercept identified, we have our slope identified, we have the standard error of both our y-intercept and our slope already calculated for us, and we'll eventually get to this in the next lesson. We also have our standard deviation of our residuals and our r-squared value. All right, now down here you can see our scatter plot. You can see our residual plot, which shows no additional pattern, and you can see the histogram of the residuals. Now for letter A, what is the equation of the least squares regression line for predicting the amount of tip from the length of the stay? And we need to define any variables that we use. Now, the predicted tip is going to equal our y-intercept, which is at 4.535, plus our slope, which is found right next to our explanatory variable, which is time in minutes. So plus our slope of 0.03013 times the time in minutes. Right? This is your equation. Now, for letter B, interpret the slope and y-intercept of the least square regression line in context. Now remember, slope is the change in y over the change in x. And because this is written as a unit rate, the change in x is always 1, and the change in y is always the value of the slope. So for our slope, the predicted tip increases by about $0.03013 for each additional minute in the buffet. Right? So predicted tip increases by our slope value for each additional single minute that's spent at the buffet. Now our y-intercept is a single point in time. So it tells us that the predicted tip is about $4 and let's say like 53.5 cents when staying 0 minutes in the buffet. Now, take a look at the minutes that we have here. We're going anywhere from a little bit above 20 minutes up to 100 minutes. 0 is pretty far outside of this pattern. It's outside of the data that was gathered, which means this is an extrapolation, so the y-intercept is not really all that trustworthy, but we can still use our slope. That's why we often do inference on slope instead of the y-intercept. Let's take a look at our next part. All right, so for letter C, interpret the values of S and R squared. All right, so S is the standard deviation of our residuals. And what it tells us is that the actual tips typically vary by about $1.78 from the values predicted by the least square regression line with X equal to the amount of time. All right, so the actual tips vary by about this much from the values predicted by the least square regression line. That's the typical prediction error. R squared is the percent of the variability in our y that can be accounted for by the least square regression line with our explanatory variable. So in this case, right, this is where I got my standard deviation, my residuals. This is where I'm getting my R squared, so that 13.2%. So 13.2% of the variability in tip is accounted for by the least squares regression line with X equal to the amount of time. Right, we learned those interpretations in chapter 3. Now letter D, interpret the standard error of the slope. All right, so the standard error of the slope tells us how far the slope typically varies from the population slope. So if we repeated the random sampling many times, the slope of the sample regression line would typically vary by about 0.02448 from the slope of the true least square regression line for predicting the amount of tip in dollars from the length of time in minutes. All right, and I'm getting that number from right here. This is the standard error coefficient, and it's the one that's next to slope, so this is the standard error of the slope. All right, so if we randomly sampled 12 receipts over and over again, the slope of the sample regression line would typically vary by about 0.02448 from the slope of the true regression line. That's our interpretation. Now the final part of this is, well, almost final part, for letter E is to calculate and interpret a 95% confidence interval for the slope of the population regression line. All right, so let's take a look at this. For our statement, we want to do what we did previously in intervals, and we want to identify our confidence level and then define the parameter that we want to use for our interval. So my confidence level is 95%, so I want to construct a 95% confidence interval for beta, which is equal to the slope of the true regression line relating y equals tip to x equals time at this buffet. My plan for this is to do a t-interval for beta. Now I need to check my liner. For linear, there is no leftover curved pattern in the residual plot. We had already looked at this earlier. All right, so it's safe to use a linear relationship for this. For independent, we can assume that 12 is less than 10% of all receipts from this buffet in one night. For normal, the histogram of the residuals shows no strong skewness or outliers, as you can see here. For equal standard deviation, there is no clear greater than or less than pattern within the residuals. All right, so there's no clear less than or greater than pattern in the residual plot, meaning that the points are pretty evenly scattered above and below this residual equals 0 line. And if you take a look at this, it looks like the center of the residuals here is at 0, and that is pretty evenly spaced out on either side. And for random, a random sample of 12 receipts was taken, so all of my conditions are met. Now from here, I need to go through and calculate my interval. So my degrees of freedom are going to be my sample of 12 minus 2, which is 10. I need to calculate my t star, and to do that, I'm going to use inverse t. I have a 95% confidence interval. That means that I need 2.5% for each of the tails. That would be 100 minus 95, which is 5, divided by 2 is 2.5. And turning that from a percent into a decimal for my area gives me 0.025. So over here, I'm going to hit second vars to get to distribution. I'm going to go down to inverse t. My area is going to be 0.025. My degrees of freedom 10. Paste this in. And I get negative 2.228 approximately. Now, my t star is always going to be positive. I'm basically looking at the absolute value of this. So although my t is negative, my t star is going to be written as the positive 2.228. Right? And now I just start filling things in. My slope is this 0.03013. So that's what I'm putting in place of b. My t star is this 2.228. Goes right here. And then my standard error of my slope is the 0.02448. That goes right here. And then I just typed all of this into the calculator. I typed this in first with subtraction, and I got negative 0.02441. And then I typed all of this in with addition, and I got 0.08467. All right, so my conclusion is that we are 95% confident that the interval from negative 0.02441 to positive 0.08467 captures the slope of the true regression line relating y equals tip to x equals time. And for the final piece of this, for letter F, based on the interval, is there convincing evidence of an association between length of stay and tip amount in the population of receipts? And explain your answer. Well, if there is a relationship between these, if there's an association, then we should have a slope that's either an interval of slopes that's either all positives or all negatives. And when you take a look at this interval, it includes negatives, 0 is included within the interval, to positives. A horizontal line is a slope of 0. A horizontal line has no linear relationship because y is no longer changing with x. So because 0 is in the interval, there is not convincing evidence of an association between length of stay and tip amount in the population of receipts. Go ahead and try these problems, and I'll see you in class.